So uh, today we start differential equations of first order and first degree. Before we get into the first order, first degree differential equations, we will actually discuss what differential equations are and how do you calculate the degree and the order of the differential equation. So some basics first. Yeah. So what is the basic definition? So an equation involving independent and dependent variables and one or more derivatives of the dependent variables with respect to the independent variables is called a differential equation. Examples. So first, let's say dy by dx is equal to x by x square plus 4. So this is a simple differential equation. It has what is the independent variable here? Independent variable is x, dependent variable is y, and independent variable is x, dependent variable is y, and we have a derivative of y with respect to x. So this is one example. Now there can be more, like we can have x square plus 1 dy by dx is equal to y square plus 1. So here we have dependent variable y, independent variable x. So we have terms containing um, independent variable and the dependent variable and the derivative. Okay. Then suppose we have like this. So it is not necessary that you have only first derivative. You can have second derivative or higher derivatives. We can also have it in the like this. This is the third order. So you have first order derivatives, you can have second order derivatives, you can have third order derivatives and raised to different powers and so on. Also, we can have in the form of differentials. So we have dx and dy, we can have as differentials. So all of these are differential equations. Now, generally, when there is a quadratic equation, um, a polynomial equation, we have, some unknowns. Now here, what is the unknown? That is what we'll find out now. Now, differential equation can be classified into two forms. So types of differential equation. First one is the ordinary differential equation. We call in short as ODE or ODEs. Okay. Now these contain only one independent variable. And thus they will have only one dependent variable naturally. So example, all the above examples 1 to 5 above are ordinary differential equations. We just have one independent variable x and the dependent variable is y. And partial differential equation means we have more than one independent variables and we call these as PDEs. So partial differential equations contain more than one independent variables. Now, so example, oh, examples of this: x dou u by dou x plus y dou u by dou y is n times u, where u is a function of x and y. So u is a function of x and y. So we have partial derivative with respect to x, partial derivative with respect to y. So when you have partial derivatives, then it's a partial differential equation. Then we can have higher order partial derivatives. So this is also example of a partial differential equation. Okay. So there are differential equations will involve independent variables and dependent variables. Dependent variable will be one. So, and the derivative of the dependent variable with respect to one or more independent variables. That equation is called as a differential equation. So partial, two categories: ordinary differential equations and partial differential equations. Next, how do we find the order and degree? Order and degree of a differential equation. Very important, because based on this, our methods will change. How to solve the differential equation, our methods of solving the differential equation will change based on this order and degree of a differential equation. So order is simple. The order of the highest derivative appearing in the equation. Appearing in the equation, differential equation. Then what is degree? The power of the highest ordered derivative after the differential equation is written in polynomial form. That is, none of the powers uh, of the derivatives is a fraction. That is, we remove the, suppose it is 2 by 3. We will do that. We will take examples. Suppose du by dx to the power 2 by 3. We will have to cube it to remove the 2 by 3 from it. Once we do that, then we can find the um, the degree. We'll do examples. So note, very important note, if the equation cannot be written in the form of polynomials, then the degree of the differential equation is not defined. The degree of the differential equation is not defined. So let us do some examples. All right, all these examples are find the order and the degree of the differential equation. So let us do that. First one, 3x d square y by d x square raised to the power 3 minus 4 dy by dx whole raised to power 4 plus 2x square is equal to, okay, sin x, let's say. This is a differential equation. So please tell what is the order and what is the degree of this differential equation. You can put it in chat. Yes. What is the order of this differential equation and what is the degree? What is the definition? Order of the differential equation. The order of the highest derivative appearing in the equation. So highest derivative, there are two derivatives here, dy by dx and d square y by dx square. So this is the second order derivative. So order is 2 and degree. Yes, degree is the power of the highest order derivative. So highest order derivative is this. So its power is 3. So order is 2, degree is 3. Okay, good. Next, d square y by dx square is equal to 2 plus dy by dx the whole cube whole to the power 2 by 3. Tell me the order and the degree of this differential equation. What is the order and what is the degree? I'm not getting answers. At least order. Degree we will see later. What is the order? Good. Order is 2 because dy by dx and d square y by dx square. So order is 2. Now to get degree, what we need to do is we have to free this from this fractional power. This radical, it is cube root. So this radical sign has to be removed. For that, we cube on both sides. So when we cube on both sides, all right. So of course, this becomes a polynomial. You can see this. We can expand this d square y by dx square whole cube. Then we get dy by dx whole power 6 minus 4 dy by dx whole cube minus 4 equal to 0. So there's a differential equation. Highest order has power 3. So degree is 3. Order is 2, degree is 3. Now a tricky question. Y is equal to log of 1 plus first derivative of y plus first derivative of y whole square by 2 factorial plus first derivative of y whole cube by 3 factorial, so on up to infinity. What is the order and what is the degree of this differential equation? This is a differential equation. What is the order and what is the degree? Good, good. One answer. So this we should know that the term in the bracket is the power series expansion of e power x. So of course, instead of x, we have y dash. So we get e power y dash. Okay. Log of e power y dash is nothing but y dash. So this equation reduces to y equal to y dash. So you have first derivative. So order is 1. And this first derivative has power 1. So degree is 1. So order is 1 and degree is 1. Okay. Next. I will say y power 5. Doesn't matter. Yeah. What is the order and what is the degree? Answers in the chat. One answer I got. Others? What is the order at least? Order is 2, correct? Order is 2 because first order, second order, and degree. Degree is not defined because we cannot eliminate, we cannot write this as polynomial in derivatives. We cannot write as the DE cannot be rewritten as a polynomial in derivatives. So either one, suppose I remove log for this, then I'll get exponential power of e power second derivative of y. So I cannot either remove the logarithm or the exponential. So I cannot do that. So that's why it is not defined. Last one. What is the order and what is the degree? Order clearly dy by dx, d square y by dx uh, square and d cube y by dx cube. So order is 3. Degree, you have a cosine term and the log term. Cosine of the derivative, log of the derivative. It's impossible to remove it and write it in polynomial of derivatives form. So degree is not defined. Of course, these are hypothetical and imaginary kind of differential equations, what we have written. In physical formulations, differential equations are of a particular type. When we are solving, you will uh, come to know as we proceed further. Now, so we defined what is a differential equation. We categorized the differential equation into ordinary and partial derivative differential equations. And now we discuss the order and degree of the differential equation. So now primarily we are dealing with the ordinary differential equations. Okay. Now next is an important definition. What is solution of a differential equation? So solution of a differential equation. Now, what do we mean by solution of a quadratic equation? Ax square plus bx plus c. Solution of a quadratic equation means the values of x that satisfy the equation. Now, the differential equations, uh, we have a differential equation like this. Say dy by dx is equal to 3x square. This is a differential equation. Okay. Now we can see that y is equal to x cube plus some constant c will satisfy this differential equation. The derivative dy by dx, for if you differentiate, you will get 3x square. That means you substitute y in this differential equation, it will satisfy. Okay. So the definition is like this. Definition of the solution. Now, a solution of a differential equation is an explicit or implicit function of y, the independent variable, in terms of x. Sorry, the dependent variable in terms of the independent variable. Here we are talking about, by the way, ODEs. For partial differential equation, the solution will be uh, the implicit or explicit function, whatever the function u or v or w of the independent variable, dependent variable in terms of the independent variables. So solution is a function, okay, which satisfies the given differential equation. Okay. Now note when the function is substituted in, and the function is substituted in the differential equation, it reduces to an identity. Now the solution can be of two types. We know one is the general solution. Okay. So general solution is, this is a solution of the differential equation, the given differential equation, which has arbitrary constants, arbitrary constants, okay, arbitrary constants, which in number are equal to the order of the differential equation. Now, in the previous question, the previous example here, this is order 1. So when order is 1, you will get only one arbitrary constant, because when you integrate, solution of the differential equation is obtained by integration. So when we integrate, what we get is one arbitrary constant. Suppose, let us say this was the same. Suppose instead of the first derivative, it was the second derivative given. So when we integrate, dy by dx will be 3x square plus c1. Three x square plus c1. Next, again, when we integrate second time, we get x cube plus c1x plus c2. So here you observe order of differential equation is equal to 2. The number of independent arbitrary constants are also equal to 2 in the solution. Okay. The solution should have arbitrary constants equal in number to that of the order of the differential equation. So this is called as the general solution or the complete primitive, the another word for it, complete primitive, general solution, and then we have particular solution. A particular solution means it does not have arbitrary constant, but you have to give particular values of the arbitrary constants based on some given conditions. Okay. So the solution obtained by giving particular values to the arbitrary constants. Particular values to the arbitrary constants in the general solution is called particular solution. Now, we say like, okay, for x equal to 0, y is equal to 1. Then in this equation, when you substitute x equal to 0 and y equal to 1, we'll get c2 is equal to 1. And we say derivative at x equal to 0 should be 0. Then c1 will be 0. Then the particular solution will be y is equal to x cube plus 1. So that is a particular solution. C1 is 0 and C2 is 1. So what does a solution mean? It actually represents a family of curves. The solution is a function, and for different values of the arbitrary constants, you get different functions. So it is a family of functions satisfying certain properties. So here the property is that the curvature of all such functions is 6 times the x coordinate at any given point. So this is the uh, condition. So all the curves will satisfy this condition. Second derivative as well. So the whole solution is, whole method is to find um, the whole point of differential equation is to find the solutions. How to find the solutions? So now let us move on. Now we talk about the main topic now. So far it was prelude to differential equations. Now solutions to ODEs, ordinary differential equations of first order and first degree. Solutions to ODE of first order and first degree. So methods. We'll write the summary of the methods and then we discuss. Today, if we can cover most of it, we'll see. First one is separation of variables or variables separable form. Of differential equation. So we call this as the method of separation of variables. So actually these are methods based on the form. Depends on the form, how the form is. Based on that, we do. So variable separable form of the differential equation or method of separation of variables. Now this is applicable uh, if it is not directly variable separable, but by some substitution. Now reducible by some substitution, the equation is reducible to variable separable form. Okay. So both of these are solved by what we call as the method of separation of variables. The second type is the homogeneous differential equation. We'll discuss about this. There's a homogeneous differential equation and reducible to homogeneous form by some substitution. Then we have very important, very important form. This will have, so linear differential equation. Linear differential equation, and again reducible to linear form. And next is a very interesting method. We can very easily solve if we understand that they are exact differentials. We can just directly integrate. So we'll discuss these. So the first method is the method of separation of variables. So within this is this type that actually the differential equation is in variables separable form. So what it means is, let us take this. The we'll take examples and then show it, separation of variables. So solve, for example, this one, secant square x um, tan y dx plus secant square y tan x dy. Now, this is a differential equation. What we can do, I can write this like this. I can either take this to other side or doesn't require. I can divide by tan x tan y throughout. That means left hand side and right hand side. If I do that, I will get secant square x by tan x tan y at secant square x tan y by tan x tan y. That will be secant square x tan x dx plus secant square y tan y dy. Okay. So now what we have done, this is a variable separable form. This term is purely in terms of x. This is the independent variable and this is the dependent variable. Okay. So this is the variable separable form. This is, we have separated the variables. So variables are separated into two different terms. So now when we solve, how do we solve? Integrated. So upon integration, we get integral secant square x by tan x dx plus integral secant square y upon tan y dy is equal to integral of 0. Now, integral of 0 is 0. You can omit that. Or integral of 0 can be a constant, no matter with what it is integrated. Leave that at that. Now, integral of secant square x upon tan x is log mod tan x, right? Because this is f dash x by f of x form. So log mod tan x, and this is log mod tan y is equal to some c. So from here we get log of modulus of tan x tan y is equal to c, and we can rewrite this as tan x tan y is equal to e power c, and this plus or minus doesn't matter. Now this whole thing I can replace by a single constant. So I'll write this as tan x tan y is equal to c1. So this is the solution. So I have simplified the solution like this, or we can leave it here. Doesn't matter, but this is a more elegant solution. Tan x tan y equal to c. So this is the separation of variables, variable separable form. So we can, after we separate the variable x and variable y into two different terms and then integrate. That is the separation of variables form. Let us look at the second example. Solve. Dy by dx is equal to 1 plus y square upon 1 plus x square. So solution. So you can see that we can easily, just by inspection, observation, we can see, we can separate the variables. Separating the variables, we get dy upon 1 plus y square is equal to dx upon 1 plus x square. So on integrating, so dy upon 1 plus y square dx upon 1 plus x square. So what is this? Tan inverse y is equal to tan inverse x. Of course, you should have a constant. It is a must. So we can write the constant as tan inverse c. It will be easier because we can omit the tan inverse. So we get tan inverse of y minus tan inverse of x, or we can write it in this form. If we want to write in terms of y explicitly in terms of x, then we can write this as tan inverse of x plus c by 1 minus x times c. So we get y is equal to x plus c times 1 minus cx. This is the solution. Okay. So this is this solution. Third question. So method of separation of variables. One more simple one we'll do. Solve dy by dx is equal to e power x minus y plus x square into e power minus y. So how do you separate the variables? Very easy. So we can write this as dy by dx is equal to e power x into e power minus y plus x square into e power minus y, right, like this. Then e power y, we can take this e power minus y goes to the other side. That means you take it to the denominator, and then it becomes e power y dy. And this dx we can take to the other side. So now we have converted this to two separated terms. So now integrating, we get this integral of e power y is e power y, e power x is e power x, x cubed by 3 plus c. So from here we can get y as log of e power x plus x cubed by 3 plus c. This is the solution. Okay, this is an implicit form, this is an explicit form. Now category B in this is reducible to separable variables. Reducible to separable variables form. Okay. So let's take an example. So this was 3. Let us take this as 4. These are a little difficult. I'll give a simple one. All right. Okay, dy by dx is equal to sine square of x plus 3y plus 5. Now directly They are not in variable separable form. Now, if you see this, okay, you may get, "Arey, what to do with this?" But what we can do is let u be equal to x plus 3y. So what we get is du is dx plus 3 dy. Okay. Now, so du by dx will be 1 plus 3 dy by dx. Okay. So dy by dx. So substituting here. So we have done substitution. Substitute. So therefore the original equation becomes original so dy by dx is du by dx minus 1 times 1 upon 3 is sine square u plus 5. So we get du by dx is equal to 3 sine square u plus 15 plus 1. So 3 sine square u plus 16. So now we can do separation of variables like this. 3 sine square u plus 16 is equal to dx. Now, this is a kind of a standard form. We can convert it. Okay. To solve this, divide by, cos square u in the numerator and denominator. LHS, left hand side. So you get secant square u du upon 3 tan square u plus 16 secant square u. But 16 secant square u is 1 plus tan square u. So 16 plus 3, we get 19. 19 tan square u plus 16 dx. Now we can integrate. So now when you do a substitution, tan u, tan square u, tan u as t, so put tan u equal to t. I'll take this 19 outside. Secant square u du will be dt. And this is t square plus 16 upon 19. So this is 1 by a tan inverse x by a. That form we'll get. So you get 1 by 4 root 19 tan inverse root 19 by 4 t, you have to substitute tan u. Okay. Now u, originally what was our substitution of u? X plus 3y. So we get 1 upon 4 root 19 tan inverse root 19 by 4 tan of x plus 3y is equal to x plus c. This is the solution. So things may get involved, but you can solve. What did we do is we substituted. By substitution, the form which was not separable variable, we reduced to separable variable form. So this is the method of separation of variables. Sometimes it is much more easier to do. Now, this is the one of the fundamental forms, this one methods, separation of variables. Now let us look at the next type, the homogeneous differential equation. Now, what is the homogeneous differential equation? Now, the ODE of this form dy by dx is equal to a function of x comma y upon function of another function of x comma y if f and g are homogeneous functions of the same degree. Okay, the ODE of this form, I'll write like this, is called homogeneous if g and f and g are homogeneous functions of the same degree. So how to solve this kind of a problem? Method to solve. Rewrite the ODE in one of these forms. Either dy by dx is some function of y upon x, or dx by dy is a function of x upon y. So then substitute here y is equal to ux, or y by x is equal to u. Then you can convert to variable separable form, or here substitute x by y is equal to v, and then substitute. We'll be able to do. So let's look at some examples. So within this category, the first example, solve x square y dx minus x cube plus y cube dy. When you carefully observe, uh, the degree of the first term, other than the derivative, omit the derivatives, look at the expression. This is of degree 3, and each of these terms are of degree 3. So we can write this dy by dx as x square y by x cube plus y cube. Take this to the other side and write dy by dx like this. Now we can write dy by dx if we divide by the highest degree term of x, that means x cube. If we divide by x cube, numerator and denominator, then what do we get? Dy by dx is equal to y upon x by 1 plus y upon x the whole cube. Now we have converted this to this form, f of y upon x. So therefore, now substitute y by x is equal to u, which means y is equal to ux, which means dy by dx is equal to u plus x du by dx. So replace this in this equation. Therefore, the ODE transforms to u plus x du by dx is equal to u upon 1 plus u cube. Now, after that, we can convert to separable variables form. Let us see this. X du by dx is equal to u by 1 plus u cube minus u. So we get u minus u to the power 4 by 1 plus u cube. So u and u cancels. So we have x du by dx is equal to minus u power 4 by 1 plus u cube. Now we can separate the variables. 1 plus u cube upon u power 4 du is minus dx upon x. Separation of variables. So a form like this we can separate out. So this now solving, integrating, we can write solving or integrating. It means the same thing for differential equations. So I will write this integral as u power minus 4 plus 1 upon u du So this is u power minus 4 plus 1 minus 3 upon minus 3. U power minus 4 plus 1 by minus 4 plus 1 plus log u is equal to minus log x. And if required, we can write as log c. That may be easier. So that we have to write a constant. The constant can be anything. So we are writing the constant as log c, because if I eliminate the log, it will be easier. So what I get if I merge these, I get log u plus log x plus log c is equal to, this minus becomes plus 1 upon 3 u power minus 3. Okay, so we get log of u x c is equal to 1 upon 3 u power minus 3. Now substitute back u as y upon x, or y is equal to ux. So this means we get log of yc is equal to 1 by 3 y upon x whole to the power minus 3. So this right hand side is 1 by 3 x by y whole cube. So c times y is e power 1 by 3 x by y whole cube. This is the solution. So there's a solution. So what did we do here? We observed that it is a homogeneous equation. The numerator is of degree 3. It's a degree 3 term. X has degree 2, y has degree 1. So together product, the degree is 3. Denominator, both the terms are of degree 3. So this is a polynomial in x and y. This is a polynomial in x and y and of degree 3 each term. So by dividing by x cube, we converted to this form and then we substituted u and we solved. Okay. The concept, if we get, the steps are not a issue. Concepts, we just have to get it right. Okay. One more. Now reducible to homogeneous. So solve. X plus 2y minus 1 dx is equal to x plus 2y plus 1 dy. Now, interesting. This is, so of course we can write dy by dx, dy by dx is equal to x plus 2y minus 1 by x plus 2y plus 1. Now this is a homogeneous expression. This is numerator is a linear degree 1 polynomial. This is degree 1 polynomial. Okay. Of course, here one thing we can directly do is write this as u, x plus 2y as u. Okay. And we can do this. So put x plus 2y is equal to u. So we get 1 plus 2 dy by dx is equal to du by dx. So this implies du by dx minus 1 upon half. is equal to u minus 1 by u plus 1. So now it is by substitution, and now I can easily solve this. Sometimes what happens is, suppose you have a degree term, uh, s- you know, you can intelligently uh, shift to the point of intersection. You can substitute to the point of intersection. This problem is simple here. It's a homogeneous form, but directly I can do separation of variables like this. Now du by dx is, take this to the other side, 2u minus 2 upon u plus 1 plus 1, which is 2u minus 2 plus u plus 1 by u plus 1. So du by dx is 3u minus 1 by u plus 1. Now we can separate the variables. U plus 1 by 3u minus 1 du is dx. And this is like a partial fraction kind of a thing. So integrating. Now I'll write the step like this. 3u minus 1, 3u minus 1 uh, plus 7, no, plus 4. So what do I get? 3u plus 3. So what I did, 3u plus 3, I have written as 3u minus 1 plus 4 on purpose, and divide this upon 3. So what I get in the numerator is 3u plus 3 divided by 3, I'll get u plus 1. So this u plus 1, I am writing as 1 by 3 times 3u plus 3 and 1 by 3 times 3u minus 1 plus 1. This is, separating to partial fractions. That's all. So this will be 1 by 3 integral 1 plus 4 upon 3u minus 1 du integral dx. So what we get is 1 upon 3 u plus 4 by 3 log 3u minus 1 x plus c. If we want, we can write log. And now substitute, u as x plus 2y. So take 3 to the other side, x plus 2y plus 4 times log of 3 times x plus 2y minus 1 is equal to 3x plus 3c. So there's a solution. So bring x this side, you get twice of y minus x plus 4 times of log mod, in fact 3x plus 6y minus 1 is equal to 3c. That 3c we can convert to c1. So this is the solution. Okay. So this is, I'm covering these fast because I'm not going through many examples, but this is very important. We get problems of linear differential equation of first order, first degree. Mostly it is separation of variables. Now, next is a very, very important model is this I'll spend time with linear differential equations. Of course, linear differential equation, first order, first degree. The definition is like this simple definition. In a linear differential equation of a first order, the dependent variable and its derivative occur in first degree and are not multiplied together. That is y and dy by dx do not appear as a product in any term. Okay. So standard form. So standard form of linear differential equation of first order. We have higher order linear differential equations, very important models, those are. But standard form of first order is dy by dx plus p function of x, py is equal to q. So, or we can have dx by dy plus py of x is equal to q of y. In the first case, the dependent variable is y. In the second case, the dependent variable is x, and the independent variable is y. Okay. Now, very important is observe this. This p of x and q of x can be any function, polynomials of any degree, sine, cos, that is trigonometric, logarithmic, exponential, anything. It doesn't make any difference. It will function can be called as a linear differential equation. We can have x power 10 also here. doesn't make any difference. X power 15 doesn't make any difference. This is still a linear differential equation because the order of the derivative is 1, the first order derivative, and its degree is 1. And y, the dependent variable, appears in a separate term other than dy by dx. So this is of degree 1 and dy by dx is of degree 1 and they are not multiplied together. So this is the differential equation. Okay, this is the linear differential equation. Now there is a full solution procedure. Now, okay, I'll explain how do we get this. Dy by dx is equal to plus p of x times y is equal to q of x. Now we introduce a term called integrating factor. So as of now, we don't know how to integrate it. Okay. So see this, the method to solve the above let rho of x be a function such that when multiplied to the equation, the left hand side LHS becomes the derivative of rho of x comma y. Okay, that is rho of x is such that rho of x dy by dx plus rho of x into p of x y, okay, is equal to d by dx of rho of x y. So what we call it as, the left hand side is the total derivative. Okay, we call like this. This term will come total derivative. Of course, we have done it in partial derivatives. So what we have done is we are considering, we have to find that rho, what that rho is. Rho is such that when you multiply rho to the differential equation, the left hand side becomes the total derivative like this. Therefore, the linear differential equation becomes, upon multiplying by rho, we get d by dx on the left hand side is equal to rho of x into q of x. So now we have done separation of variables kind of thing. D of rho of x dy is rho of x into q of x dx, which means, which implies, so now integrating both sides, when we integrate 1 with the derivative of some function u, which is rho of x into y. Okay, what we get is this. So left hand side is we get rho of x into y. 1 times this is the differential. So integration will give you rho of x into y is equal to integral of rho of x to q of x dx, say plus c. So we have solved this. So this is purely a function of x. We solve this and this is the solution. So this is the solution of the differential equation. So we have found y. Now, so what is this rho? Now, because upon multiplying, because rho of x is a factor which makes the integration possible, we call, very important, rho of x as the integrating factor. We call this as the integrating factor. Okay, if. So to find if, now to find rho of x, what is this rho of x? So let's go back here. So our assumption was that multiplying rho of x to the left hand side of the differential equation, rho plus rho of x p of x times y is the total derivative of rho of x into y. So let's expand the right hand side and see what we get. We get rho of x dy by dx, no problem, plus y times derivative of rho of x. So here, this term and this term are cancelling. And then once they cancel, once that is cancelled, then y and y also get cancelled. So we get p of x is d rho by dx. Very interesting. So from here, we get rho of x as integral of p, sorry, not just p, we have rho of x into p of x is this one. So by separation of variables, we get d rho by rho of x is p of x dx. So integrating log rho of x is equal to integral p of x dx. Therefore, omitting the constant, because for anything it can be the same, rho of x will be e power integral p of x dx. In fact, I can write this as log c, and this will be c times e power integral rho of x dx. And because rho is a factor which is multiplying the total differential equation entirely, okay. So c, the constant of this doesn't matter, okay. It may be 1, 2 or anything, doesn't matter. So without loss of generality, we can take the constant as 1. Therefore, we get this. So now we have a interesting term. This all explanation. Now I'll write the final way how to see the solution. Therefore, the solution of the differential equation, linear differential equation, dy by dx plus p of x times y equal to q of x is, see here, what is the solution? Rho of x into y. So I will write this as integrating factor times y is equal to integral of integrating factor times the right hand side function dx plus c. Here, integrating factor times the dependent variable equal to integral of integrating factor times the function on the right hand side plus c. Okay, where the integrating factor is e power integral p of x dx. This is the solution. This is to be remembered. If you don't remember those steps, doesn't matter, but you should know what is the concept of integrating factor. Integrating factor is that function of x. When you multiply throughout the differential equation, the left hand side becomes the total derivative. And then after that, you can easily integrate it. So the solution is this: integrating factor times y is equal to integral of integrating factor times q of x dx plus c. Now, similarly, if it is for y, similarly, the solution for the differential equation dx by dy plus p of y times x is equal to q of y is integrating factor times x, the dependent variable, minus integral of integrating factor times the right hand side function plus c, where the integrating factor is equal to exponent of the integral of this function p of y dy. This, I'm sorry, this will be with respect to y. Okay. This is the linear differential equation. Okay. So let us take one or two examples. Solve. X square minus 1 into dy upon dx plus 2xy is equal to 1. So here, so solution, of course, see, this is not in homogeneous form, nor is it in variable separable form. So now if you observe this, I can write this as, we can rewrite the differential equation as dy by dx plus dividing throughout by x square minus 1. So you get 2x by x square minus 1 times y is equal to 1 upon x square minus 1. So this is of the form dy by dx plus p of x times y is equal to q of x. So p of x is this, q of x is this. So where p of x is 2x by x square minus 1 and q of x is x square 1 upon x square minus 1. So what is the integrating factor? Integrating factor is e power integral of p of x dx, which is e power integral of 2x upon x square minus 1 dx. So this is e power log of x square minus 1 integral. This is f dash x by f of x. The integral will be log of x square minus 1. So e power log of x square minus 1 is x square minus 1. So the integrating factor is x square minus 1. Okay. The integrating factor is x square minus 1. So therefore, the solution is integrating factor times y is equal to integral of integrating factor times q plus c. Okay. So integrating factor is x square minus 1 times y is equal to integral of x square minus 1 times 1 upon x square minus 1 dx plus c. So we get x square minus 1 times y. This cancels. Integral of 1 is x plus c. This is the solution. This is the solution of the above linear differential equation. Of course, you can just see that the first order derivative and the dependent variable are appearing in degree 1 and they are not multiplied together. So this is a direct indication that it's a linear order linear differential equation. Even before we converted it to this form, we can identify that way. Okay, is this clear? One more problem and we'll stop for today. Solve. Cos square x dy by dx plus y is equal to tan x. So again, dy by dx and y appear in separate terms and are of degree 1 and they're not multiplied together. So we can do this. So we can rewrite this as dy by dx plus y secant square x is equal to tan x times secant square x. So this is p of x and this is q of x. So dy by dx plus y times p of x plus is equal to q of x. So this is a linear differential equation of first order, first degree. So now uh, integrating factor is integral is e power integral p of x secant square x dx. So integral of secant square x is tan x. So this is the integrating factor. Now let us multiply solution. Therefore, the solution is y into integrating factor, or integrating factor into y is integral of integrating factor times the right hand side function plus c. So e power tan x times y is equal to e power tan x times tan x into secant square x dx plus c. To solve the right hand side, put tan x equal to t. So e power t into t secant square x dx will be dt plus c. Now we can do integration by parts. First function times integral of the second minus integral of the derivative of the first. This is the first function, this is the second function, into the integral of the second. So we get t e power t minus e power t plus c, which is t is tan x here. So tan x times e power tan x, or I should say t minus 1 times e power t. So tan x minus e power tan x. So this implies y is tan x minus tan x minus 1 plus c times e power minus tan x. So this is the solution. Okay. So this was the differential equations. What did we discuss? The separable variables form. We discussed the homogeneous form and the linear differential equation form. Linear differential equation has some more important forms. And then we have exact. So yesterday I missed the class. If time permits, I will take on the weekday, say after 7, maybe 7:15 to 8:15 on 2 days. Okay. Thank you.